That's such a nice lady who says that all the time. Okay, so with thermodynamics, it's really about a couple of things. Thermo means heat, and then how heat moves around, but it also means how chemical reactions are affected by heat. That was the original concept. So Le Chatelier's principle is what we were doing at the end of the previous chapter. So what you need to do, if you have a problem like this, what happens to the ammonia concentration when the nitrogen concentration is increased? So the idea is that this chemical reaction has already gone to equilibrium. It's just sitting there. Doesn't go to completion. That's why you have the two directional arrow. And so the forward direction is equal to the rate in the reverse direction. That's why the concentrations don't change with time. So now it's at equilibrium, and otherwise you wouldn't be able to do anything. But if you apply a stress to it, then it will shift because it still has to be equal to this equilibrium constant. So here's the first example. What happens to the ammonia concentration when the nitrogen concentration is increased? So the stress is that the nitrogen concentration is being increased. So I always put the stress on the bottom, and then I have to decide which direction it's going to increase or decrease. Which direction is it going to go? So if I'm adding more reactant, you would expect to push the reaction that way to turn it into product. So using that logic, I say that the arrow is going in that direction. Once the arrow starts going in that direction, I can see that everything over here is going to increase, and everything over here is going to decrease. So if you look at this one, this was the one that was stressed. You added more of that. This one decreases because every time one nitrogen molecule goes that way, it has to take 3 hydrogens with it. So the concentration of hydrogen is going to go down. And the temperature will go up, and the ammonia concentration will go up. If we look at its effect on the equilibrium constant, that totally makes sense. So to keep this a constant, keep the number the same number, if I increase this, I could counteract that mathematically by decreasing this or by increasing this. So that's the whole concept. So on the exam, you'll probably have a problem that's similar to this right here. So there were several examples of that. And then we learned about rates, but this was just a preliminary about the rates. But to review some of the stuff that we had talked about, here's the energy of the reactants, the energy in the products. So when the reactants go to the products in this chemical reaction, you give off this amount of energy. Okay, so that represents that energy right here, right? So if you add a catalyst or whatever, it doesn't matter. The energy of the reactants is still the same. The energy of the products is still the same. So the difference between here is what determines the equilibrium constant. So here's 2 ways to look at that. Delta G, or the change in free energy right here, is equal to this manipulation of mathematical representation of the equilibrium constant. So the rate is determined by this activation energy right here. So if I were to put a catalyst in here, it doesn't change reactant energy or product energy, so it doesn't change this at all. What it does is simply lowers this bump right here, making it easier to get to the products, so it goes faster. It also makes it easier to get from products back into the reactants. So the thing about adding a catalyst, it simply makes it go to equilibrium faster. It doesn't change the point of equilibrium. If I increase the rate in that direction, I also increase the rate in that direction. And then collision theory in the transition state is a very simple concept. Nothing mathematical about it. So these two things have to collide. They have to collide with the right orientation and the right energy to get into the transition state. And the transition state is the highest energy right here because these bonds are halfway broken, these bonds are halfway formed. And because of that, you're not meeting the octet rule and the duet rule. So if they make it past the transition state, then they fall back down into a lower energy compared to that and goes to form products. So, and I gave a couple of examples. So an enzyme, for example, I'm a biochemist. I will give biochemical examples. So if we think of a catalyst, it could be a simple thing like an iron atom or a tin atom or anything like that. But an enzyme is a little bit more complex. So here's the enzyme. And so my whole point being is that the reactant binds to the enzyme. It's attracted to the enzyme because of millions of years of evolution of the enzyme. So what happens is when they come into close proximity, they bond to each or bind to each other, not chemical bond. How do they get attracted to each other? Well, it's Londons, it's dipolar, it's hydrogen bonds, and ion to dipole type attractions. So enzymes concentrate the reactants on the catalyst, bringing them into close proximity. So if there was more than one reactant, it brings them into close proximity to each other, which really has the effect of concentrating the reactants, and you know the effect of that on the rate constant. And then it puts them into the right orientation. So now every collision is going to be fruitful. And it puts strains on the bonds to be broken. And it adds chemical groups that perform the function such as supplying electrons or changing the pH or whatever it is. So my point here is that if I put a bunch of acidic amino acid groups on the surface of this protein right here, the effective pH right here is going to be way different than out here in the media. Here's an example of how an enzyme uses something like folic acid to help it do its job. So what an enzyme does, what any catalyst does, is it changes how the transition state happens. It makes it into a lower energy transition state so it's easier to get to the products. So how it does that, it's actually intimately involved in how electrons go from point A to point B, all that kind of stuff. So here would be the effect of a bad inactive enzyme on a metabolic pathway. It can be actually devastating. Then this is the part where we did reaction rates. So reaction rates are quite simple. The rate for this reaction right here in the forward direction is equal to some rate constant times the concentration of A and times the concentration of B. So looking at that, that means that A and B have to collide with one another. If I were to increase the concentration of A, there's going to be more collisions statistically. If I were to increase the concentration of A and B, then I will get even more collisions and the rate will go faster. And then the reverse rate is equal to a different rate constant times the concentration of two of C's that have to collide with one another. So just combining like terms because they just so happen to be the same molecule, then it becomes squared. So you can see just like with putting equilibrium constants together, the rate constants are similar. If two of these are required, then the concentration is squared. So then I took a specific example of hydrogen peroxide. So here's the rate going into the forward direction. And what we're saying here is that it's proportional. If I double the concentration of hydrogen peroxide, it about quadruples the rate. But if I want to use the equal sign, then I have to get rid of the proportionality sign using a proportionality constant right there. So where do we get that proportionality constant? Well, mathematically, we just look at the rate compared to what concentrations were used. So if I had a higher concentration, I'll get a faster rate. But within a certain range, that will be consistent, and that will be a constant. So then I just want people to know what is a rate. So using that same chemical reaction, we start off in a container with only hydrogen peroxide. Then we let it decompose into water and into oxygen. So here I'm looking at the time after I initiate the reaction, and I'm looking at one of the products. So at 0 time, there is no oxygen. But as time goes on, I start to make oxygen. So eventually, this rate right here will start to fall off because I'm running out of hydrogen peroxide. So what we do is take the rate where it's still straight right here, where it's proportional. So we take the slope of that straight line right there, and that gives us the rate. So in this case, it was millimoles of oxygen per minute. That was the rate. So here's some things that affect reaction rates, the concentrations, the temperature, and catalyst. And I use an example of the enzyme called catalase, which all of you have because you are all aerobic organisms. So hydrogen peroxide can be broken down by iron. That's why you see if you have a cut on your skin and you put hydrogen peroxide in it, you see it bubbling. It's bubbling because of oxygen being evolved. And then catalase, which is an enzyme that's meant to protect you against hydrogen peroxide so that it doesn't form hydroxyl radicals and cause all kinds of problems to your DNA and everything else. We have an enzyme called catalase. And catalase took advantage of this pre-existing chemistry. And look at the cofactor of this enzyme right here. It's the iron atom. So if it sucks the hydrogen peroxide right into there, because of the design of the enzyme, these are now attracted to each other, it pulls it right up against that iron atom and causes it to decompose. So the idea, if this doesn't collide directly into this right here, if it collides over here, it gets sucked into that active site of the enzyme, pulls it right up against that iron atom, causing it to immediately decompose. And what I'm trying to do here is to show you the two definitions of equilibrium. One is that at some point in time, the concentrations of reactants and products don't change with time anymore. But what's in fact happening is that the rate in the forward reaction is decreasing as you run out of reactants. The rate in the reverse direction is increasing as you make more products available. And the point of equilibrium happens when those two rates are the same. That's equilibrium. The rate in the forward direction is now equal to the rate in the reverse direction. So I use that definition to show you how the equilibrium constant is really described is the relationship between the different rate constants. So constant divided by a constant is a constant. So here, just showing you that equilibrium constant in the forward direction is the inverse of that of the reverse direction. Then, anybody have any questions so far?
No.
Then this right here, I put it in a red box. I kind of changed some of the things I was doing because of the virus. But I won't ask you to do this on the exam. But if you have one concentration at equilibrium, you can use stoichiometry to calculate the others. So here you made two solutions, you mix them together, nothing has happened yet. And then when it goes to equilibrium, you did have 2 moles per liter of A, now it's 1.8 mole per liter of A. What happened to the 0.2 moles per liter of A? Well, it went that way. 2 of these makes 1 of those. 2 of these makes 3 of those. So here's how you can get how much is left. How much is made. Then 2 of these takes 1 of these with it. So 0.2 would take 0.1 of B away, leaving it at 0.9. So that would be 0.9, that would be 0.1, that would be 0.3. Now you have all the concentrations at equilibrium. That's all you need to get the actual equilibrium constant. And there was another example there. So I wanted to give you an introduction to this stuff. It can be very complicated, and my point is that it's not. It's really just turns into some definitions. So G and H and S are all forms of energy. We could write energy diagrams with anything over here, okay? So I put here potential energy as either G, H, or S. But G is called usable energy or free energy. That's the amount of energy that can actually be used to do work. So now here's an example. Octane being burned in oxygen to produce CO2 and water and heat. Octane is a minor component of gasoline. So here's the actual number. That's the G for 2 molecules of this and 25 molecules of that. Here's the G for 16 molecules of that and 18 molecules for that. And if you do the subtraction, you take this and you subtract this, because that was what they decided to do. The difference right here is negative 13,000 kilojoules per mole. And this is what determines the equilibrium constant. And this is the transition state right here, which in a chemical reaction would be indicated by the arrow, right? What it means, if you have a negative delta G, that means that it's an exothermic reaction. It's going to happen. We often use the word exergonic and endergonic if we're actually talking about G. So if we look at entropy, changes in entropy were this. We went from a liquid to a gas. Then we took these 2 gases right there and we heated them up, which then caused their volume to expand. So we took advantage of that to get work done from this gasoline type reaction. So we need a machine to harvest that energy to do work. So here we're taking advantage of the change in temperature, which causes the gases to go faster, which then pushes down on the piston. Now we change the volume and we're able to actually do mechanical work. And it's not that different in a protein. So oftentimes we will use ATP. And if you notice ATP, the delta G is negative 7.3 kilocalories per mole. So here's the machine, one of the machines, skeletal muscle. So here's the thick filament is the myosin, here's the thin filament. And you look at the two Z bands right here, they're far apart. And during contraction, after you're hydrolyzing ATP, after calcium comes rushing into the skeletal muscle cell to cause the hydrolysis of ATP, you see the muscle proteins simply slide into each other like this. And that causes a shortening of the muscle, which causes work to be done. So what we're really doing is causing a conformational change in the myosin. The conformational change is simply rotation about a single bonds. So for example, I put ATP in here, I hydrolyze ATP, the introduction of calcium, and that hydrolysis of ATP causes one part of the molecule to move against the other. This is mechanical action right there that ultimately does the work of our muscles. And here's another example doing the work of moving ions from one side of a membrane to the other. So again, it's a conformational change in this membrane protein right here. Anyway, so let's see. Let me now find, unless you have questions, let me get the homework for that. Come on, where are you? So again, just work backwards. Come on, open. Okay, so here's the last homework. Oh shoot, sorry. It's not what I wanted. I want the answer key. Okay. So I won't put this on the exam, but here I did pretty much everything except tell you what that was right there. So starting with this, then you have this at equilibrium. So that means that some of this had to go that way. And for every one of these, I make 3 of these, right? So if this is 0.2, then that's 0.6. Once you have these concentrations, you just plug them into the equilibrium expression. Mathematically, the way I would do this mathematically, well, first of all, you see the 0.6 and the 0.6, so you can just cancel that out. So that essentially becomes 1 divided by 0.2 and then divided by 0.6. If these weren't the same, an easy way to do this on your calculator is simply 0.6 times 0.6, divide by 0.2, divide by 0.6, divide by 0.6, and then divide by 0.6. So anybody have any questions on any of these, Le Chatelier's principle type problems?
I have a question. When would it ever be unchanged?
Never.
Okay.
Yep. So here's the rate, right? The rate is equal to some rate constant times the concentration of this reactant times the concentration of this reactant raised to the second power. Because you have three things that have to collide to get into the transition state. So the rate will depend upon the concentrations of all three of those things. It just so happens that these happen to be the same. So it's mathematically squared. And then here, oh, what's happening here? Something didn't show up. Oh, I see, because one's a gas and one's a liquid. Okay. So if this is a gas and everything else is a gas except for water, right? The rate in the forward direction will be equal to some rate constant. That concentration raised to the fourth power, that concentration raised to the second power, that concentration raised to the ninth power. And when it's a liquid, and we leave out pure liquids, pure solids, then we would leave this out. So the idea is that you got this liquid with a whole bunch of phosphorus trihydride, and above that liquid is some hydrogen and some oxygen. But the reaction is actually taking place in the gaseous phase. So this is so in big excess and it's a pure liquid, so the rate isn't dependent on it. And, let's see, some questions about this. The idea here is that this is an exothermic reaction. There's more potential energy here in the reactants than there is in the products. So where would that energy go? It would be given off to the environment. So that same reaction is exothermic, it gives off heat. The delta G would be negative 25 kilojoules, and it's exergonic. Okay. So is it a spontaneous reaction? The answer is yes, because this is higher energy than this. So any questions about that homework? I'm going to try a new button. See if it will work. Nope. Now, 5. Okay, so this is homework 25. It's on acids and bases. So homework 26 was the only one that was on that last chapter. But maybe I'll just go over this anyway. So which of the following would make a good buffer pair? So what do you want a buffer to be? It's a weak acid and it's a weak base. So A, hydrochloric acid is on your list of strong acids, so that's not going to work. And this is not going to change the pH either. Because if hydrochloric acid is an extremely strong acid, that means its conjugate base, the chloride ion, is going to be an extremely weak base, not do anything. But here's a weak acid, here's a weak base. Here's a strong acid, so that's not going to work. Here's another strong acid, so that's not going to work. Here is a weak acid or a weak base, and that would be a weak base. So yeah, that would work. So a buffer was created using ascorbic acid and sodium ascorbate. So this would be the strong acid. Here would be the formula for it. And sodium ascorbate would be the conjugate base. So here's the formula for that. So here's the reaction. And so what I need to do is get the Ka. So the Ka is simply products over reactants. And I want the pH, so what I have to do is solve for the hydronium ion concentration. So I did that right here. And then just plug in all my numbers. So here is Ka. Here's, this is where I'm hard with being dyslexic. Here's that, and then the original one was that. So that's, where am I? Whatever, can't see it, dyslexic. So then I crunch all these numbers. And of course, the way I would do that in my calculator is this number times that number, then divide by that number. So there is the actual hydronium ion concentration, and the pH is simply the negative log of that number. Okay. Any questions on that? This one was very similar. And of course, these problems, I give you the answers so that you make sure you're doing it right. Unfortunately, we won't do that on the exam. So there's several buffer problems there. So then what I'm trying to get you to do is be good at writing the equilibrium constant expressions. So if you're doing this in the forward direction, here's the products on top, here's the reactants on bottom. If we're going for the reverse direction, then the definitions of reactants and products are now the opposite. We're going in that direction, so these are the products and these are the reactants. We do the same thing, don't we? And another thing that I was trying to emphasize is that these should be the inverse of each other, because the definition of reactants and products are just switched. So here's another stoichiometry problem. And so what I did is, just to give you a little bit of a secret, for the biochem students, they had to actually figure this out. The Chem 100 students, how do I get them to be able to do this? Well, I just gave them those numbers. So I didn't have to do all this part. So this is the stoichiometry. You went from 1 molar chlorine to 0.5, so 0.5 disappeared. Where did it go? It went that way. So 2 of these make 2 of those, so 0.5 made 0.5. For every 0.5, every 2 of these, I make only 1 of these, so this should be half of what that is. Then, for every 2 that go that way, it takes 1 of those with it. So if 0.5 went that way, then 0.25 of this went that way. So we have at equilibrium 0.75. And this is products over reactants, put in the numbers, crunch the numbers. Assuming you don't have questions. So what about this one? Similar type of thing. Here we went from 1 mole per liter to 0.3. So that means that 0.7 went that way. So this, it doesn't matter because it's a solid. We're not going to use it anyway. So if 0.7, excuse me, if 0.7 goes that way, for every one of these, I make 2 of these. So that should be 1.4. And then for every 0.3 that goes that way, I have to take 0.3 that goes that way. So that means that there's 0.7 left. So put them in here, crunch the numbers, and then that's the answer. And this was Le Chatelier's principle. So here's the equilibrium. So it's at equilibrium. And then what do? Well, I added acid to it. What does acid do? Here's the acid is involved in equilibrium right here. So if I add acid, I'm really essentially increasing the hydronium ion concentration. So if I increase a product, I'm going to make the reaction go in the other direction to make more reactant. So once I get this arrow set, everything over here is going to increase. Everything over here is going to decrease. Because every time 2 of these go that direction, it takes 1 of these with it. Then what happens to the sulfide if the pH increased by adding hydroxide? Well, if I add a hydroxide, it immediately reacts with hydronium ion. So I'm essentially reducing hydronium ion concentration. A very simple way to look at Le Chatelier's principle is it's sitting there at equilibrium. Whatever you do to it, it tries to counteract what you just did to it. So what we did is we took away hydronium ion, so it tries to replace it. A little bit different explanation is that I'm taking away this, and every time I take away this, I need these 2 guys to come over here to replace it. So once I find that direction right there, that everything over here is going to decrease, and everything over here is going to increase. So questions?
Nope.
You guys make me feel so inadequate. Right now, I got so many things open on the computer. Close that. Close that. Close that. Close that. That did not open. Okay, there we go. Okay, so here's homework 24. So what I was trying to get you to do over here is simply get good at writing the equilibrium expression. So it's products over reactants, and I leave out water. Same thing over here, products over reactants, leave out water. So notice the difference right here. So in reality, if I were to take carbonic acid and put it in water, sometimes it will do this, sometimes it does this. Mostly you're going to end up with this, but then again, that depends upon the pH. The same thing over here, but here we call it a KB because here it's acting like a base. Here the hydrogen carbonate is taking a hydrogen away from water to form carbonic acid, and when it does that, it leaves the hydroxide. That's why I call it the KB. Similar thing for over here. And then this was just labeling acid, base, conjugate acid, and conjugate base. So all we're doing is looking, where does the hydrogen ion go? It goes from here to here. So that's the acid, that's the base. When I take water and I put an H+ on it, I get hydronium ion. But now if I want to go backwards, the hydrogen goes from here to the acetate, meaning that that's the acid on this side, that's the base on this side, but they're on the product side, so we call them conjugates. So here's the acid and its conjugate base. Here's the base and its conjugate acid. And equilibrium constant for that reaction. Equilibrium constant for this, so products over reactants. Notice that water is a pure liquid, so it was left out. And then calcium carbonate was a solid, so it was left out. And notice that the 2 here shows up as an exponent, right? So here's another one. So aluminum hydroxide would dissolve in water to give you aluminum and 3 hydroxides. So KSP, which is simply, anytime you see a capital K, that's an equilibrium constant, right? So it's simply products over reactants. But because that's a solid, it's left out. So now if I actually have the values for that, if I measure the values, I can put them in here and get an equilibrium constant. So it's called the solubility product because you're simply multiplying these things, all the ones that are soluble. So by the way, this would be a saturated solution. You understand what I'm saying about that? I get some water. I try to dissolve the solid in there, but not all of it dissolves. Whatever doesn't dissolve just goes on the bottom and we don't care about it. So what is in the solution could be a saturated solution. Here's the concentrations of that saturated solution. So calculate the equilibrium constant and then find the missing concentrations. So here's what we had. We started off making a solution of 1 mole per liter, but when we actually looked at the solution, we didn't have 1 mole per liter, we had 0.9923. So what we're missing is 0.0077 moles per liter. And where did it go? It went that way. So one of these gives me one of those. 0.0077 gives me 0.0077. And then this would be twice the amount as this. So products over reactants, and then plug in the numbers, and then there's your answer. So here's an acid. This is acetic acid. So we made a 1 molar solution of acetic acid in water. And then what we found is that at equilibrium, it was 0.99600. So can you understand why acetic acid is considered a weak acid? It doesn't go very far in this direction. Do you see how we get the numbers? These numbers would have to be the same, right? It's just stoichiometry. So here I'm showing you the stoichiometry. So we got the moles per liter of acetic acid used. I want to convert that into moles per liter of acetate, get rid of moles per liter of acetic acid. And that's simply the stoichiometric conversion factors that are 1 to 1. So what do I need to get the pH? This is all I need to get the pH. That is the hydronium ion concentration. So the negative log of that is about 2.4. So then the Ka would be simply products over reactants at equilibrium. There's your number. So this is a small number, which means that you have mostly this and a little bit of this, and that information is seen right here. At equilibrium, it's almost entirely in the unionized form. So here's another one like that. Calculate the equilibrium constant for an acid. And in this case, I was being a little bit more tricky. I'm giving you the pH of that solution. What does that do for you? Well, the pH can be directly converted into the hydronium ion concentration. That's how I got that. And then the stoichiometry. Every time I make one of these, I'll also have to make one of those. Okay. You could have also got that same information by just doing this subtraction right here. See how that works? So these are just mathematical functions. And what is it based upon? Equilibrium constant. What is that based upon? Stoichiometry. And this last one right here is a titration. So calculate the concentration of an HCl solution if 100 milliliters of this HCl required 33 milliliters of 0.2 moles per liter magnesium hydroxide. So here's the chemical reaction that we would need. So I have enough information to get the moles of the base. I got the volume and the concentration. I don't have the concentration for the acid. So I have to start the problem with getting the moles of the base. So here I did that. 0.033 liters, 0.2 moles per liter gives me that many moles of magnesium hydroxide. Then I use stoichiometry to convert moles of the base into moles of the acid. So I did that. Here's the moles of the base, and I got 2 moles of HCl for every 1 mole of magnesium hydroxide. That's the stoichiometric conversion factor. Now I have the moles of the HCl. But that, we were told, was in 100 milliliters of water. So to get the concentration, it's simply the moles that I calculated divided by the liters that they gave me. There's our concentration. So, let's see. Not hearing anything. I'll go to 23.
Yeah, I think 24, I was pretty confident in that chapter,
Yeah,
in that homework. Yeah.
good. I wish I was confident making it. Okay, so you had 3 homeworks on acids and bases, right? So here's the first one. This is just naming them. Okay. So here's a non-oxy acid, right? So we name it like hydrochloric acid. Here's an oxy acid. So to name that, we have to know the name of the polyatomic ion. So that's sulfite. So if it ends in an ITE, then it ends in an OUS acid. Sulfate ends in an ic acid. Okay? And that's just acetic acid. It's actually its common name. To give it a more systematic name, we have to go to organic nomenclature, which we're not doing. If you take the second semester of that, that's what we start off with, is doing organic chemistry. So here, complete the reaction. Yes, that's a strong acid in water, so it's a one-directional arrow. It goes to completion. So what is the pH of a 0.001 molar solution of HCl? Well, as soon as that touches water, it's gone. It's completely turned into products. So this would be 0.001, and so would this. So now that I have hydronium ion being 0.001, then the pH is simply the negative log of that, which is now pH 3. So here's a base. So sodium hydroxide is very soluble in water. Many of the other hydroxides are not. So we have a complete reaction. And what is the pH of a 0.001 molar solution? Well, again, if it's going completely soluble, then this is gone and it's 100% in this form. So that means that hydronium ion concentration is 0.001. Did I say that right? Hydroxide ion concentration is 0.001. What would be the hydronium ion concentration? Here I'm using Kw to calculate what is the hydronium ion concentration. Once I have that, I simply take the negative log of it. So you know what I mean by this? This is Kw. Kw is the OH concentration times the hydronium ion concentration, and that equals 10 to the minus 14th. So here, complete the reaction. So notice that I put a 2 here. In a one-directional arrow, that means that everything is going to go all the way. Now, in fact, more precisely, there would be a little bit of HSO4 over here, but I just left it out. Not a significant amount. So what is the pH of a 0.001 molar solution of this diprotic acid? So here's the concentration of the acid. I got 2 moles of hydronium for every 1 mole of sulfuric acid. So here's the concentration of hydronium ion. Get the pH, simply the negative log of that. So there's the pH. And while we're at this, I might say something about pH. So here you see this number is 4 significant figures, right? Here's the 4 significant figures right here. That 2 refers to the power of 10. Okay? That's what that refers to. So oftentimes you see textbooks start using really kind of rounded off looking numbers. The reason is it's very difficult to measure a pH to that many significant figures. Okay. Usually it's maybe, I don't know, 3 significant figures, not usually 4. So oftentimes you will see in chemistry them ignoring things like HSO4 and all of, you know, stuff like that. So it completes the reaction. So here's magnesium hydroxide. It's going completely into solution. Now, if you look back at the solubility rules, is magnesium hydroxide completely soluble? And the answer is no. But at low concentrations, that is below the concentration of a saturated solution, yes, it will 100% go into the solution. So what is the pH of this? Well, we see 0.001 moles per liter go this way. So that's magnesium is 0.001. Hydroxide would be what? 0.002. So here I'm using the stoichiometric conversion factor to get that number. Then again, I'm using Kw to turn the hydroxide concentration into hydronium ion concentration. Plug in the numbers, there's my hydronium ion concentration, take the negative log of that, here's your pH. Okay. So here we got, in this problem compared to this problem, we calculated, where are we? Hydronium ion concentration, right? We calculated the hydroxide ion concentration. And what about the pOH? What do I need? Because I'm already given the pH. Wait, no, did I? Yeah, I gave the pH. What is the pOH? Well, I could get it by several different ways, using the square of death. I'm just trying to now integrate these kind of procedures with really the square of death. So here is acid base and conjugate acid and conjugate base. So for the most part, when we see a polyprotic acid, what do? We take off only one hydrogen ion. So same thing over here, take off only one. So I'm going H plus from here to here, so I'm making the hydronium ion and the dihydrogen phosphate. So here's the acid, its conjugate base would be that. Here's the base, its conjugate acid would be that. And again, how do I figure out which acid and base? Well, here's where the hydrogen has to go from here back onto here to get back to those reactants. And similar thing over here. Okay. So here's another titration. So a student titrated 250 milliliters of a 0.1 molar solution of sodium hydroxide. What does that mean? You got the moles per liter and the liters there. You can get the moles of the base here against a solution of H2SO4. Okay, so how do we start this problem? We have the moles of the base. Then we use stoichiometry to turn moles of the base into moles of the acid. This is simply the stoichiometric conversion factor. Now we have moles of the acid. But that, we were told, was in 221 milliliters. So to turn that into moles per liter, I simply get the moles and divide by the number of liters, and there's your answer right there. And this looks so simple now. But again, here's a diprotic acid. How many hydrogens come off? Only one, right? Then it says products over reactants. So any questions with that one? And then you also had 3 homeworks on concentrations. Maybe I'll do homework 21 first. My computer will operate. Okay. So remember in Unit 4, the last chapter in Unit 4 was basically moles per liter. Then in the next unit, Unit 5, in the next chapter was on all different other kinds of concentrations. So here, a saturated solution of salt was made by adding 36 grams to 150 grams of water. There was 5 grams of salt on the bottom that did not dissolve. So what is dissolved in the water? Not 36 grams, but 31 grams. So we had 31 grams of salt dissolved in 150 grams of water. Okay. So get grams per gram, multiply by 100 to turn it into parts per 100 is about 21%. That's the percent solubility. So here, 2 miscible liquids were mixed to the point of saturation. So in other words, you take water, maybe you take some alcohol, and you add it, you mix, you add it with mixing, then you can't get it anymore to mix. You start to see 2 layers now. One layer is the solution, and the other is the other liquid that won't dissolve into it. So now you know it's saturated. So they found that there was 25 milliliters of liquid A could dissolve in every 350 milliliters of the solution. So what is the percent volume per volume? Well, we got 25 milliliters of A dissolved in every 350 milliliters of the solution. Then turn that into parts per 100, it's about 7%. And then, to point out that this is actually a conversion factor, how many milliliters of A are there in 25 milliliters of the solution? So notice I'm using the units to my advantage. I'm writing 25 milliliters of the solution. And this tells me that there's 7.1 milliliters of A in every 100 milliliters of the solution. So I'm canceling out milliliters of the solution, getting milliliters of A. So I took 15 grams of sodium hydroxide and added it to 185 grams of water. What is the percent mass per mass? So 15 grams of the solute, and this should be grams of what? The solution. That includes 15 grams of the hydroxide and 185 grams of the water. So then multiply by 100, it's 7.5%. And using that as a conversion factor. So how many grams of sodium hydroxide in 444 grams of the solution. So that's 444 grams of what? The solution. So I need to cancel out grams of the solution and keep grams of the solute. So how many grams of water in 500 grams of a 0.1 moles per mass per mass solution? So I got 500 grams of what? The solution. So I need to get rid of grams of solution, keep grams of hydroxide, so that's 0.5 grams. So if there's 0.5 grams of the solute, 500 grams, how many grams of water did you have to add? Well, it's simply a subtraction, right? So a chemist found so many grams of a pesticide in 2 liters of water. What is the percent mass per volume? Okay, well, mass per volume is always grams per milliliter. So I got that many grams, and I had to convert liters into milliliters, and then simply divide, multiply by 100. So there's the percent mass per volume. So what is the concentration in parts per million? What do I need to get parts per million? I need to get grams per milliliter and multiply by 1,000,000. Does that make sense? So percent is parts per 100. I multiplied by 100. ppm is parts per million, so I multiplied by 1,000,000. How many milliliters of 6 parts per million solution are needed to make 4 liters of 0.1 parts per million solution? So in other words, this is a dilution problem. Because I'm going from 6 ppm to 0.1 ppm. That's a dilution, right? So I have to figure out what are my variables. So the concentration of the concentrated one, 6 ppm. This must be the concentration of the diluted one. So the volume of the concentrated is what I'm looking for. So the volume of the diluted one is going to be 4 liters. So I'm just mathematically solving for VC. Plug in my numbers. And notice that ppm cancels out, so the unit is simply liters. But they wanted milliliters, so I had to convert into milliliters. What was the dilution factor? Well, we went from 6 to 0.1. So if I move the decimal place over 1, move the decimal place over 1, cancel out moles per liter is 1 to 60. If I didn't have an easy way of doing that and I just passed that step or something, I would get a numerical value, a decimal value. But even that can be converted into that because that's the same thing as 0.01667 over 1. But what we would like to do is to get the upper number to be a 1. You can't always do that, but we try. So I divide by itself, both sides, so I get 1 to 60. So how many milliliters of a 10% volume per volume ethanol solution are needed to have 20 milliliters of pure ethanol? So here's my conversion factor. That's the concentration. And this is 20 milliliters of ethanol, right? So 20 milliliters of ethanol. Get rid of milliliters of ethanol. Keep milliliters of the solution. That's the conversion factor right there. and I get 200 milliliters of the solution. So how many grams of sodium chloride? 6 million milliliters of a 20% mass per volume solution. So again, I have to analyze to find out where is my conversion factor. It's right here, right? 20 grams of sodium chloride in every 100 milliliters of the solution. And this is what? 6 million milliliters of what? The solution. Okay. So cancel out milliliters of the solution. Keep grams of sodium chloride. There's your answer right there. So how many grams of TCE in 6 milliliters of a 10 parts per million solution? So again, 10 parts per million is my conversion factor. That's the concentration. So this is 6 milliliters of the solution. I want to get rid of milliliters of solution, keep keep grams of TCE. So there's my answer. So how many milliliters of a 10 parts per million TCE solution are needed to have 1 gram of TCE? So again, that's my conversion factor, right? 1 gram of TCE, I need to get rid of grams of TCE, keep milliliters of the solution, and there's the answer. Okay. 22. So the last homework on solutions. So how many grams of magnesium chloride in 30 milliliters of a 25.5 parts per trillion solution? So this is 30 milliliters of what? The solution. This is 25.5 grams in every trillion milliliters. Okay, so there's your answer. So for a 25% mass per volume solution, what is the molarity? Okay, so I got 25 grams in every 100 milliliters, right? That's the same thing as 250 grams in every 1,000 milliliters, which of course is a liter now. And what do I need to do? Convert grams into moles. So here's the molar mass, or the gram formula weight. So that gives me 2.63 moles in every 1 liter of the solution. What is the osmolarity? Well, when I take magnesium chloride and dissolve it into water, 1 mole gives me 1 mole of magnesium ion and 2 moles of chloride ion, which altogether is 3 moles of dissolved particles, which is 3 osmoles. So that is our conversion factor. So I got 2.63 moles per liter. I get rid of moles, keep osmoles. I got that many osmoles in the liter.
Professor,
Yeah.
well, on the first question, how do you get 10 to the power of 12? Because I got 10 to the power of 3 because I thought parts per thousand would be 10 to the
Oh,
power
no,
of
it's parts per trillion.
trillion. Oh, ha, got it.
Yeah. Did you ever take
Okay, well, that answers my question.
did you take oceanography
Huh?
before?
In high school.
Yeah, yeah. They use PPT for parts per thousand in oceanography.
Mommy.
Oh, okay.
Yeah. I was confused by that too, by the way. Okay, where were we? Oh, the normality then. So we already figured out that this 25% mass per volume solution is that many moles per liter, right? So now all we have to do is get moles into equivalents. So again, we get this equation for dissolving magnesium chloride. What is an equivalent? It's a mole of charge. So we get 1 mole of magnesium ion at 2 equivalents per mole, or we get 2 moles of chloride ion at 1 equivalent per mole. In either case, it's 2 equivalents. So that's the conversion factor. 2 equivalents per mole. So I'm simply canceling out moles, getting equivalents, and then turning that into the symbolism for that, which is capital N. So how many equivalents of magnesium ion in 6 moles of magnesium phosphate? So I have to get this equation so I can get the conversion factor. 1 mole of magnesium phosphate is equal to 6 equivalents, either of magnesium or of phosphate. So I got 6 moles of magnesium phosphate at 6 equivalents per liter gives me this. And notice that I could do it in different ways. Here I went from moles into equivalents directly using 1 to 6 as our conversion factor. Then I did it a different way. I went from moles of magnesium phosphate into moles of magnesium. Then I looked at the equivalents just in the magnesium. There's 2 equivalents for every mole of magnesium, but I get the same answer either way. And then let's see, 5. So if I got 36 equivalents of magnesium, then I would need 36 equivalents of phosphate to make that a neutral solution, right? Notice how it's all a direct proportion. 6 is the 6, as 36 is the 36. So how many moles of magnesium ion in 6 milliliters of a 6 equivalents per liter magnesium phosphate? So I need the equation so I can figure out what they're asking. So 1 mole gives me 6 equivalents. So I got 6 milliliters. I turn that into liters. And I'm going to use this to turn that into equivalents. I'm always going to use this as the conversion factor. So that means I got that many equivalents. Okay, now what are they asking for? Well, they're asking for moles of that. So 1 mole of magnesium phosphate has 6 equivalents, so there's the number of moles for magnesium phosphate. So now they want not moles of magnesium phosphate, but they want moles of magnesium. So I just use the conversion factor from the equation, right? For every 1 mole of this, there's 3 moles of magnesium. So here's how I got that conversion factor, and then there's the final answer right there. Yes, then you could do it different ways too. But you'll end up with the same answer. So now we're looking at osmoles. So again, for a magnesium phosphate solution, 1 mole of magnesium gives me 5 osmoles. That's the conversion factor. So I got 6 milliliters, so I turn that into liters. And then my conversion factor is equivalents per liter. So I got that many equivalents. And then I turn equivalents into moles, magnesium phosphate. So now I'm here. I just need this conversion factor to convert moles into osmoles. There's the final answer. So this is about colligative properties, the last couple of problems. So what happens to each of these when solute is added? Now notice that this is the vapor pressure of the solvent, boiling point of the solvent, freezing point of the solvent, and osmotic pressure of the solvent. So say I'm looking at water. I add sodium chloride to it. What happens to the vapor pressure? It goes down. Comes to the boiling point, it goes up. The freezing point goes down, and the osmotic pressure goes up. What if I'm not talking about water? What if I'm talking about, say, ethanol? And I add, what could I add? Well, one way to make hand cleaner is you take ethanol and you put in some glycerol. So glycerol just makes it so it doesn't dry your skin up too much, right? And ethanol kills the virus. So what happens to the solvent, which is ethanol? Well, the vapor pressure will go down, the boiling point would go up, the freezing point would go down, and the osmotic pressure would go up. And is no change even possible? Nope. So draw an arrow to show which direction that each of the 3 electrolytes, in other words, solutes, will diffuse across the membrane. So first of all, we're talking about solutes, right? We're not talking about the solvent. So this is dialysis. And so diffusion goes from a higher concentration to a lower concentration. So sodium would diffuse that way, or dialyze that way. Phosphate would dialyze that way. And potassium is going to go both ways. Just because these are the same concentration means that nobody sends a guard to the semi-permeable membrane and says, hey, you guys can't go here anymore. It's just that the rate in one direction is now equal to the rate in the other direction. This last one, draw an arrow to show which direction solvent will flow across the membrane. So if we're talking about solvent, now this is not dialysis, this is osmosis. So what will happen to the cell? Okay, here I have more solute, right, than here. If I got more solute over here, what does that tell me about the solvent? More solute means less solvent. So that means that there's more water in the cell than there is outside the cell when I put the cell into this solution. So water is going to osmose out of the cell into the solution and cause the cell to shrink. So anyway, that's all of the homeworks. Any other questions on the homework?
Nope.
know.
So let me ask you a question. What was more valuable, going over the chapter or going over the homework?
The homework.
Yeah, I would say the homework too.
Homework? Okay. Now that I'm not sharing the screen, let's see the chat. Okay, so it's 3:30 already, but I'm not that tired. You want me to do something else? Want me to go through any of the other chapters, or what do you guys like? You're tired, you just want to go to sleep, or you want me to go, you want me to go over another chapter, or what would be cool? So the exam's going to be open on Thursday and Friday. You've got a couple days to study. So you can always email me questions if you come across any.
Okay.
Quick question. Is the grade on our grade book our current grade, or is that like the curved grade?
No,
Our
grade
curved-
book is out of control.
Okay.
If I spent 20 hours a day trying to figure out how to make grade work well, then I might be able to figure it out. But that's one of the things that I need to, on that committee, to try to fix. Gradebook is a problem because, yeah, it's really hard to do weighted stuff. So what I normally end up doing is I put everything into an Excel sheet so I can actually do weighted stuff and throw out stuff and count things half as much and things like that. Gradebook can't really do all that.
So the grade on our grade book is not necessarily the grade we have in your class.
Nope.
Okay.
If you got a 9.5 out of 10 on the homework, then that's true. But
Yeah.
but there's
But
nothing
the overall
weighted.
part.
Yeah, there's nothing weighted on that. Yeah. But anyway, it's interesting that you asked that, because always at the end of the semester, students say, well, what do I need to get an A? What do I need to pass? And it's like, well, why are you even asking me that? Because you got one more thing to do, and that's the last exam. And no matter what I would tell you, what should be your attitude? Simply do the best you can on that exam. You can't do any better. I can't imagine me telling somebody, oh yeah, don't study very hard for the final. You know what I mean?
Yeah.
So I know it's
So if I
stress and
have
all
a
that
B
stuff.
right now, does that mean I have like an A, or or do I have to wait for the final?
Well, I mean, if you have a B compared to what? What's on
So
grade?
on gradebook it says I have a B, but so that technically doesn't really mean I have a B, right? Would that mean
No,
that I
it does not mean that at
higher
all.
am?
So if you want to know how I grade, go back and look at the introduction.
Mm-hmm.
Pretty well detailed there. So you've had your first 4 exams. So now I can go look and find out which is your lowest one. And that lowest one will count only half as much as the others,
Okay.
including the final. Yeah. But I don't have all the information because I don't have the final. So with your homework,
Okay.
there was 26 possible homeworks. I'll probably go and throw out maybe the worst 5, and then take the average of that, and that's 15% of your grade. Then I look at all the extra credit stuff. That could be up to 5 points added to whatever your average is. So you'll get a weighted average from your homework and exams.
Okay, cool.
And yeah, so then you could have up to 5 points added to that.
Nice.
Yeah. Okay, well, anyway. Let's see. Yeah, John doesn't like Sakai. Yeah. Several years ago, they thought about changing to a different platform. And those different platforms, none of them were perfect, and all of them were way more expensive. And the good thing about Sakai is at least it's open source, and that's what I have to do with this committee. With this committee, we're going to be working with the actual experts. So I'm a user, and I'm going to be telling the experts what we need, and they'll tell me what can be changed and what cannot be changed. And then I'll go to the vice president for academic affairs and tell them, they told me they can't do that, but you tell them they're going to do that. And then maybe it will become better. But yeah, you're right. It has a lot of limitations, but all of them do.
So Professor, I'm sorry. I just want to be completely clear because I can't find the email that you sent about the due dates changing. Are you accepting anything for late homework? I understand that like it's pushing everything back for you, but like you can see I've never submitted anything late and I literally can't find the email. But
Well, the email comes after I make in the announcement. So it's in all the announcements.
So it's like an email and an announcement, or it's only under announcements?
It's
'Cause
both.
I can't. Okay,
When
well I didn't look.
When I post an announcement, there's an option to notify everybody, and they
Yeah.
do that by email.
I mean, I read all my emails, but I get like a lot of emails every day now, especially with all the COVID stuff. But I pretty much use testing quizzes to like keep track, and everything's scheduled in my planner. So last week I looked at it and I seen it and I scheduled it for today because I had 2 finals today. So it's just like, I just need to know pretty much if you're not gonna let us turn anything in. I just need a solid answer because I missed earlier.
Well, all the answer keys are posted. So, yeah.
Okay, cool. Thank you.
Yeah, sorry. So do you guys want me to do another chapter, or you want the time to study?
I'm good.
I'm sorry?
I think I'm good
Okay.
for now, at least. I'll email you.
Yeah. Yep. Okay, well, I'll get this up on the YouTube channel. You guys want to hear something funny about YouTube channel? So I
Sure.
found out that one of my nephews, who's, well, I think he turned 12, Saya, he loves to go spearfishing, like 3-prong stuff. He has his own YouTube channel. I saw it yesterday. Yeah. So I can't wait to tell him that I have a YouTube channel as well.
Can watch you.
It's called Catch and Eat. It's pretty funny. Okay, well, anyway, you got questions? Just let me know.
So I just want to confirm that the final's still on Thursday, Friday, 9 a.m. to 9 p.m., making sure
Yep.
I didn't miss any emails.
Certainly
Cool.
is.
Thank you.
Okie dokie. Okay, well, you guys have a great day then.
Thank you. Bye.
You folks.
Thank you.
Thank you. Bye-bye.